So I've saved one section, which is kind of a difficult section until the end. But even as a difficult section, it's not as difficult as the difficult parts of chapter 22. So suppose that we have an extended charge. So this charge is spread out over some volume. And I want to find what's the electrical potential right there. Well, that means I have to find some little dq that is some r away, and then I got to integrate over all the dq's. So that means we got a little dv here, and that's going to be integral of k. So be dq over r. And we just integrate over all of that. Now, the nice thing about this is, yes, it's an integral. Yes, if dq is in 3 dimensions, this is a triple integral. Okay, so it sounds really nasty, but it's not a vector integral. And we know that vector integrals are part of what makes it tough. So this is just a regular straight triple integral. Okay, so let's do an example here. Let's do a line of charge. So the line of charge has some charge per length lambda on it, and it's length minus L to L, and I want to know if I'm at some spot right here, some distance d from the middle of it, what is the electric potential right there? Okay, so we got some little dq right here. That dq is going to be some distance r away. Now, remember, when we did this with vectors, we had to find the components that added up. We don't have to do that now because there's no components. It's not a vector. So all we have to do is say that the voltage is going to be the integral dV. So that's going to be equal to the integral of k sub b dq over r. Okay, so we need to know what's dq. Well, dq is going to be lambda dx. Okay, and so again, this is straight from chapter 22, so nothing different there. What is r? R is going to be the square root of x squared plus d squared. Okay, because there's x. Okay, and so we're going to go from minus L to L. So there's the origin right there. So that means that we have, this is now the integral from minus L to L of k sub b lambda dx divided by square root x squared plus d squared. So that's going to be the integral, the k sub b lambda integral from minus L to L of dx over square root of x squared plus d squared. So how do you do that integral? Well, you look it up. Look in the back of the book. If you look in the back of the book, it says that the integral of dx over square root of x squared plus a squared is going to be equal to the natural log of x plus square root a squared plus x squared plus a squared. Okay, so that you find that in the back of the book. Okay, and so that means we can just apply that. Okay, so V is k sub b lambda times the natural log of x plus square root x squared plus d squared evaluated from minus L to L. Okay, so all you gotta do is just plug that in right there. So that's going to be k sub b lambda natural log. Okay, well, we know that the log of we subtract two logs, log a minus log b is log a over b. So if we apply that here, that's going to be equal to L plus square root L squared plus D squared divided by L divided by minus the other one, so minus L plus square root L squared plus D squared. Okay, And so there we have it. Okay. And so, so from minus L to L, there's the natural log right there. And so all you have to do is plug in the values. Okay. And so there we have the voltage. Now that's way, way, way easier than what we did before. Okay. So this is a line of charge, distributed charge, and that makes it really simple. Well, let's do another example. Let's say that we have a ring of charge, and the ring of charge is some radius big R, and we are some Z away from it. And I want to know what is the voltage at that spot right there. Well, all we got to do is the voltage is equal to the integral of dq, rather k sub e dq over r. Well, r is that. Okay, so what is r? Well, r is the square root of z squared plus r squared. Okay, and so this comes out to be, well, gosh, that's a constant. Because r is a constant, z is a constant, so that means this is just k sub e over r integral dq. Well, that's going to mean that this is just k sub e q over r. So in other words, this is going to be k sub e q over the square root of z squared plus r squared. Bam. Done. Okay. Again, this is vastly simpler than when we had the idea of trying to do this as a vector integral for electric fields. So let's do one more example. Okay, since we're on a run here, let's consider a disk of charge. And so the disk of charge, we're some z away from it. And so we'll say the disk is some radius capital R. And so we say, well, gosh, I want to know what's the electric potential right there. Okay, so dV is going to be the integral k sub e dq over r. Well, imagine we're integrating a whole bunch of little rings of radius r. Okay, so we've done that before. So we would say that dq is going to be equal to sigma times 2 pi r dr. Again, nothing really mysterious here. Okay, so the only problem is that r is not the same as this r. That's r prime right there. So r prime is going to be square root of z squared plus r squared. Okay, and so our integral now is going to look like, if we plug all that in, so that's going to be r prime down here. So that'll be that. So if we plug in our v, sorry, it should have been a v, not a dv up there. So the v is going to be equal to integral k sub e times sigma 2 pi r dr divided by square root of r squared plus z squared. And so some of this comes out of the integral, k sub e comes out, sigma comes out, 2 pi comes out. We're integrating r dr over square root r squared plus z squared from 0 to big R. Well, we look at it and say, well, gosh, that's actually not that hard of an integral to do. Okay. Because when we look up in the back of the book, integral of x dx over square root x squared plus a squared is just square root of x squared plus a squared. Okay, so that means this integral k sub e sigma 2 pi, the integral is now going to be equal to square root of r squared plus z squared evaluated at 0 and r. Okay. That means that the electric potential is going to be 2 pi sigma k sub e times square root of r squared plus z squared minus z. Okay. Unless you just want to rewrite k sub e as 1 over 4 pi epsilon naught, and then you could rewrite this as sigma over 2 epsilon naught times the square root of r squared plus z squared minus z, if you would rather do that, because that's really just saying the same thing. But in either way, we have now, in just this one little 10.5 minutes that I've been talking, we introduced the idea of distributed charge, doing an integral, and then we did what would potentially be 3 difficult integrals from chapter 22, except because they're not vectors, these are much simpler sort of things, and we found distributed charges here. Okay, and we found the electric potentials. So then all you'd have to do is just, next would be to work problems by plugging in actual numbers doing that.